Now in Calc 1, you learn a wide variety of derivative rules that you should just know, but they're also available to you on your student note sheet, which are these 24 basic rules of derivatives. Derivative of sine is cosine, for example. The derivative of e to the x is e to the x, which is rule number 9. The sum and product rules are in here, right? Sum and difference rule is number 5, product rule is number 7, quotient rule is number 8, and so on. But what we learn very quickly in Calc 1 is that these rules are all well and good. However, they don't really work without one extra companion, and that is the chain rule. And the chain rule allows us to combine those rules by nesting them one inside the other and creating composite functions, which will be differentiable as long as the interior is differentiable at, or the interior function is differentiable at x, and then that function is differentiable at that g of x value. So if it can be found, you can express it as dy over dx equals dy du times du dx. This is actually the Leibniz version. In general, in Calc 1, you don't spend too much time with that version. Most instructors kind of shy away from it and stick with the Bernoulli-Newton version. Even though Bernoulli was a buddy of Leibniz's, his notation was more a riff off of Newton. So we tend to stick with this one, which is saying, hey, take the derivative of the outside, leave the inner function alone, then take the derivative of the inside. That actually is this. It's the same part. So this part right here, take the derivative of the outside, leave the inside alone, is the part, right? It's that your inside function is u. Huh, interesting. U. I wonder if that's going to come back at any point. Like u substitution. Because of course u substitution is how we get out of having a composite function inside our integral. So u substitution is very much based on this Leibniz version. Right, so you take the derivative of the outside, leaving the inside alone, then you take the derivative of the inside with respect to x. Right, so they are the same thing, they're just written notationally slightly differently. And of course, the Leibniz version actually is what leads to its companion on the opposite side. Its opposite is u substitution for integration. I guess I should say it's inverse. U substitution for integration. Right? So that's where the u is coming from. And that's why when you look at the list of all of the derivatives, they all use u. So if you look at your note sheet, they're all using sine of u and natural log of u, because they're assuming that you're using, of course, chain rule, right? But it also helps with its opposite, which is u substitution, which is what this is using, right? Why it uses u everywhere for the basic integral reference sheet. All right, so let's find some derivatives, shall we? Let's remind ourselves of how to do this. All right, so the first thing is actually a little bit of a notation cheat, because a lot of students get this wrong because they don't realize what it's saying. So a long time ago, well, let me teach you a little lesson about mathematicians. Mathematicians are very lazy. They tend to write as few symbols as possible, and they just kind of make it standard so that everybody thinks that they know what they're saying. But as students of the subject, it can be quite difficult. So what happens here is that mathematicians are so lazy they don't want to write parentheses. So they write it like this instead. I don't make the rules, I just live by the rules, right? Okay, so if I want to find the derivative of this, I need to really be finding the derivative of this, which should let you know what the outer function is. The outer function is right here. It's the squared part. And the inner function is the g of x, which is the cosine of x part. Right? There it is. So according to our rules, we take the derivative of the outer function with respect to the inner function. Right? So you take, in other words, you take the derivative of the outer part, which is the squared part, and you leave the inner part alone. Okay. So dy dx, or if you like y prime, either one, of x, is equal to, all right, derivative of the outer part means you bring the 2 down. So 2 to the 1 power. right? So we learned that with basic power rules back in calculus. And then you leave the cosine of x alone, and then you multiply it by the derivative, so that's the 1 power. Then you multiply by the derivative of the inner part. Well, the derivative of cosine is negative sine, like that. So this is the outer part right here. And then here's the inner part nested inside, and then there's the derivative of the inner part. All right, so nobody in their right minds would let us get away with writing it like that. So we'd write negative 2 cosine of x sine of x. That is equal to dy dx. All right, speaking of notational issues, what is this one over here? So this is equal to the tangent of x to the 1/2 power. Of course, this is really a play on the fact that you have to know that anything to the 1/2 power is equal to the square root. So we just have to note the square root of a is equal to a to the 1/2 power from algebra class. All right, so that means that when I want the derivative, right, dy dx, the derivative of tangent is secant squared. Leave the x to the 1/2 alone. Right, there's the inner part. Multiply by the derivative of the x to the 1/2 part. So that would be 1/2 x to the negative 1/2. All right, well, again, I mean, this is fine. I mean, technically, they didn't ask us to simplify it. So if we're asked to leave it unsimplified, there you go. I don't know if I have room to write the word unsimplified. I ran out of space over there. Now, if they want it simplified, well, there's a couple things we could do. For one thing, we can make it secant squared of the square root of x over 2 square root of x, because of course having a negative power really means it's in the denominator. Now technically that's not simplified because there's a square root in the denominator, so you'd have to multiply both sides, both the numerator and the denominator by the square root of x. So that would be the square root of x times secant squared of the square root of x. Those cannot be squared because this is secant squared of this. This is a transcendental function, so you can't just multiply into it. So it'd be square root of x over secant squared of square root of x over 2x, because the square root of x times the square root of x down here is x. And so that's the simplified version. All right, now let's combine it. Sure. Why not have more than one at the same time? So we have this outer power. So just keep in mind what this is. This is really the cosine of 2x cubed. So it really has an outer function here, a mid function here, and an inner function here. It's one nested inside one nested inside another and nested inside another, right? So the 2x is nested inside the cosine is nested inside the cube. Okay, well at this point it's easier to think of this just with this version right here, right? You take the derivative of the outermost, right? Leave the inner part alone. Then take the derivative of the next one, leave the inner part alone, and keep working our way that way. So the outermost part is the cubed right here. So what I'm going to do is I'm going to take the derivative of that outermost part. Let me write this way. I'll take 3, leave everything else in there, to the 2 power, right? So I took the derivative of cubing. Now I'm going to take the derivative of the cosine part, right? So the cosine part's right here. So I'm going to take the derivative of cosine, which is negative sine, but then I'm going to leave the 2x alone. Right, so that's the derivative of this part. And then, of course, I have the 2x. So I would multiply by the derivative of 2x, which is 2. So you work your way into the x. You start with the outermost piece, then take the derivative of the next piece, and then take the derivative of the inner piece. So this was the double chain rule. If you're asked to leave it unsimplified, this is fine, right? So this is unsimplified. Right? Unsimplified's here. Simplified, well, there's not much really to simplify, but I could put the negative, the 2 and the 3 together and make it -6 cosine squared of 2x times sine of 2x. Just remember, if you're asked to leave it unsimplified, then I really want to see this string. I want to see the pattern written out. So just write it out and leave it there. All right, last one but not least. So let's rewrite this. This is equal to the tangent of 6x cubed to the 1/2 power. Now the thing is that the tangent is to the square root. So the tangent is on this part to the 1/2 power. So tangent is the outermost portion, right? And then the 1/2 is actually middle, right? Kind of in the middle. And then the 6x cubed is the inner part. So this is the outermost. This is the last thing that works on the x. So if you think if you were substituting a number in for x, you'd cube it and multiply by 6. Then you take the square root of it. Then you take the tangent of it, right? So tangent's the outermost. Okay, so the derivative of tangent, yet again, is secant squared. So that hasn't changed since part B. So for the derivative, dy dx, it would be equal to secant squared of, and then leave everything else alone. So 6x cubed to the 1/2 power times, all right, then we have to take the derivative of the 1/2. So the tangent's done. We've done everything with the tangent. So now we're going to do the part that involves the 1/2 power. So that'd be 1/2 to the -1/2, and then leave the 6x cubed inside alone. And now finally take the derivative of 6x cubed, which of course bring the 3 down. 3 times 6 is 18. So it'd be 18x squared. Right? Derivative of the outer, derivative of the middle, derivative of the innermost. Right? So you've got outer here, you've got your middle function here, you've got your inner function right here. And you're taking the derivative of each piece. All right, so if you're leaving it unsimplified, that's fine. Lovely. If they ask you to simplify it for whatever reason, well, let's see. 2 goes into 18 9 times. So let's think. This is the secant squared of the square root of 6x cubed. Actually, let me just write it out. Times 18x squared, and then the 2 and the square root of 6x cubed go down here. Right? All right, so not good to leave the whole square root of a 6x cubed in the denominator, but you know what you're going to do. 2 goes into 18 9, and then you can multiply by the square root of 6x cubed over the square root of 6x cubed if you want to rationalize, if you're feeling in the mood. So let's see, 2 goes into 18 9 times. So that would leave me 9x squared, square root of 6x cubed, secant squared of the square root of 6x cubed over 6x cubed, which technically isn't simplified because the 9x squared and the 6x cubed reduce. That becomes a 3, and that becomes a 2, and that becomes an x. So this would be 3 square root of 6x cubed secant of square root of 6x cubed, 6x cubed over 2x. That is the simplified version. And now you can see why a lot of the times on the worksheets and so on, we just say to leave it unsimplified, right? Because this isn't really testing your calculus skills. This is testing whether you're good at algebra, right? So testing up here is testing your calculus. Now I have to have you be good at algebra, so I will occasionally ask you to simplify it, but a lot of times I will not. So you can leave it up like that.